Ferrofluids!
Despite the extensive foundation of medical research in today's modern society and all of the advanced medical innovations that have grown from it, many methods of medical treatment are still limited and constricted in their application and processes. This is due to these treatments' inability to directly reach the targeted affected region of the body and their many unwanted side effects throughout the body due to this indirect delivery. With the possibility of deteriorating healthy parts of the body in drug administration, many medicines are known to cause a variety of side effects, and many more are simply not used.
Ferrofluids are a colloidal solution made up of a carrier solvent and ferromagnetic nanoparticles suspended in the solution. A colloid is a solution that contains nanoparticles that are evenly distributed throughout the mixture. The particles exhibit Brownian motion in that they will not settle on the bottom of the solution, rather remain suspended. The suspended particles are considered to be superparamagnetic, since although they always have magnetic moments, they only exhibit magnetic qualities in the presence of an external magnetic force when those moments align in the direction of the field. This quality prevents the particles from clumping and allows them to be precisely controlled by an external force.
It is important for the particles in ferrofluids to be on the nanoscale and to remain dispersed. In other words, there cannot be any agglomerations so that they do not fall out of suspension and so their magnetic properties do not change. Now, we need to select the specific particles that we are going to use.
There are two classes of particles we can use to form ferrofluids: ferrites and metals. Ferrites are iron oxide compounds that have long shelf lives but are not very magnetically strong. Metal particles, such as iron particles, are slightly more magnetic and are more soluble in liquids, but they do not retain their magnetic properties as well as metals. A co-precipitation method is used to produce ferrite particles. In this method, solutions containing iron 3 and/or iron 2 are used and combined with a base to form ferrites, such as magnetite, a non-toxic compound of iron oxide. Magnetite is an isometric hexoctahedral crystal. It has both octahedral and tetrahedral crystal sites, which forms a spine-like structure.
The ratio of iron 3 to iron 2 particles, the temperature, and the base used can all be changed to affect the magnetite particle size and its magnetic properties. The only downsides are that ferrite particles, such as magnetite, are slightly less soluble than pure metal particles, and that the diameter range of particles made this way can change from 3 to 20 nanometers. Pure metal particles, on the other hand, are produced by a decomposition method in which iron-containing compounds are decomposed using thermolysis, heat-based molecule breakdown, to form nanoparticles. These simple metal particles allow for a narrower diameter range of about 5 to 15 nanometers, and are slightly more soluble in liquids than the ferrites. They do, however, tend to lose their magnetic potency much more quickly. Get it? Like Ferris Bueller?
Regardless of particle used, a liquid is always needed to transfer and manipulate the particles. The liquid is called a surfactant, which is a layer of molecules that attaches to each nanoparticle so that the particles do not clump together. The surfactant can be any one of a wide range of liquids, so long as it meets a few basic requirements. Ferrofluids used in the medical field, for instance, need a surfactant with a low vapor pressure so that it does not evaporate and leave metallic particles scattered throughout the human system. The surfactant must be both effective and safe to use within the human body.
The properties of ferrofluids are much different than the properties of most typical materials. For one thing, they are not solids, and even the solid nanoparticles do not act like typical solid particles. The most critical property of ferrofluids is their magnetic structure. A magnetic field can be applied to a ferrofluid, and all of the magnetic moments of the nanoparticles will orient themselves along the field lines. This makes it easy to direct ferrofluids to particular areas. In many fields, it is also crucial for the ferrofluids to withstand nuclear radiation, which they do, without any breaking down of the substance.
While ferrofluids are currently used to improve mechanical and electrical devices, such as dampers and loudspeakers, they could potentially be used to improve drug delivery and size. Researchers are working to develop drugs coated with a thin layer of ferrofluids. Since ferrofluids go where a magnetic field is the strongest and remain there, this would allow for the drugs to be directed to a particular part of the body. Rather than infiltrating the entire body, drugs would reach their destination faster and with fewer side effects on healthy parts of the body. This type of innovation would help a variety of patients, especially those suffering from cancer. Ferrofluids would be targeted specifically at tumors, where they would stay for the necessary amount of time for the drug to take action. Patients would be able to take less of the drug, as an increased surface area of nanoparticles allows for more reactions to occur, and the reactions would occur only at the directed target.
In order to create a ferrofluid that is an effective treatment for disease, it is vital to study and alter its structure to fit the needs and parameters of the task at hand. When placing something in the body, one must ensure that the material will not perform in such a way that will inhibit or harm other bodily functions. Scientists must develop a ferrofluid that can be controlled by an induced magnetic field with precision. However, the magnetic properties of the particles must prevent them from being attracted to one another when there is no magnetic field. If clumping were to occur due to the particles' magnetic properties, not only would the particles not be able to perform their job, but also may cause other complications. The fluid must exhibit colloidal suspension or Brownian motion. This means that the particles will not settle, which will allow them to move throughout the body as directed and more effectively deliver a drug.
Ferrofluids could also help target and eliminate tumors via hyperthermia. Ferrofluids can absorb electromagnetic energy and have a high thermal conductivity. This allows them to absorb energy at a lower frequency than water, which makes up most of our body. After injecting ferrofluids into a tumor, a magnetic field could be used to hold the ferrofluid drug at the site of the tumor so that it does not disperse throughout the body. The ferrofluids could then be heated up to a temperature at which they are able to eliminate harmful cancer cells without heating up and potentially damaging surrounding parts of the body.
While ferrofluids seem to have a bright future in medicine, there are some clear limitations. Since ferrofluids are superparamagnetic, so without the presence of a magnetic field, they have the freedom to go anywhere including unwanted areas of the body. Luckily, one of the plus sides of ferrofluids is their increased surface area. Therefore, we do not need large amounts of them to do the same job as standard medicine. If any problems were to occur, the remaining particles in the body would be absorbed easily with minimal complications. Ferrofluids offer hope to researchers, doctors, and patients alike. However, they have not yet been approved for in vivo testing and therefore may have unknown harmful effects on our bodies.